Today, we're diving into one of the most interesting families on the periodic table, Group 15. Now, I know what you might be thinking. A column of elements sounds a little dry, but trust me, this family is packed with drama. We're talking a standoffish giant, a dangerously reactive sibling, and a story that affects literally everything, from the food on your plate to the fuel in a rocket.
And this whole story kicks off with a really interesting puzzle. Think about it. The air you're breathing right now is about 78% nitrogen. It is everywhere. And yet, to get our plants to grow, we have to pump the soil full of nitrogen-based fertilizers. So how can something be so incredibly abundant, but at the same time so completely out of reach? Well, the answer lies in the unique personality of this family's leader.
All right, so first things first, let's get the formal introductions out of the way. This family's official name is the Pygnictogens. Yeah, it sounds a little intense, and honestly, for good reason. It actually comes from a Greek word that means to choke, which is a pretty direct hint about what happens if you try to breathe pure nitrogen gas.
So here they are, the whole family all lined up. We start at the top with the nonmetals, nitrogen and phosphorus. Then, as we go down, we hit the metalloids, arsenic and antimony. They're kind of like the teenagers of the group. Not quite one thing, not quite the other. And we finish up with a true metal, bismuth. You can see this really clear trend happening. The further down the column you go, the more metallic these elements get.
So let's start with the head of the family, nitrogen. And if nitrogen had a personality, it would definitely be aloof. It's just incredibly stable, super unreactive, and, it generally prefers to keep to itself. Now, the reason for this aloofness is all about how it hangs out in the air around us. It's almost always found as dinitrogen, or N2. Those two nitrogen atoms are locked together by a triple bond. The best way to think about it is like a stubbornly strong, three-layered handshake. And believe me, they are not letting go of each other.
And that handshake, it's not just a cute analogy, it is incredibly strong. It takes a massive amount of energy to pry those atoms apart. We're talking over 940 kilojoules per mole. In chemistry, that's called the bond enthalpy, and it's one of the strongest bonds known for any molecule with two atoms. This is why all that nitrogen in the air just floats around, not really reacting with anything.
Okay, so this brings us right back to our original puzzle. If all the nitrogen in the air is locked up in this super strong N2 molecule, how on earth do we get it into a form that's actually useful? For fertilizers, for life itself. How do we break that handshake?
Well, the answer is one of the single most important chemical processes ever invented, the Haber-Bosch process. This is basically the recipe for taming nitrogen. You grab nitrogen from the air, you mix it with hydrogen gas, and then you apply some serious brute force. We're talking extremely high pressures, like 200 times what we feel every day, and high temperatures, over 400 degrees Celsius. Throw in an iron catalyst to speed things up, and boom, you get ammonia. This one process is credited with sustaining the food supply for almost half the people on Earth. It's a huge deal.
Okay, now let's meet the next sibling. And this is where the family dynamic gets way more interesting. Because if nitrogen is the aloof, stable one, phosphorus is its complete opposite. It's wildly reactive and forms the foundation for some incredibly energetic chemistry.
What's so fascinating about phosphorus is this idea of allotropes. It can exist in a bunch of different physical forms, kind of like it has different moods or personalities, even though it's all the same element. Let's look at two of its most famous forms.
And the contrast here is just stark. On one hand, you've got white phosphorus. It's a waxy, super reactive, and poisonous solid that can literally just catch fire on its own in the air. It's dangerously unstable. But if you heat it up carefully, it rearranges its atoms and becomes red phosphorus, which is way more stable and totally non-poisonous. It's the same element, just in a much, much calmer mood. The reactivity of phosphorus compounds is legendary. Take phosphine, or PH3. It's a highly poisonous gas with a, let's say, memorable rotten fish smell. And oh yeah, it can explode if it comes into contact with even a tiny amount of an oxidizing agent. This is not a chemical you want to be casual about. But here's the really cool part. That danger can be harnessed for good. The way phosphine just bursts in a flame is used in something called Holmes signals. They're basically distress signals for ships. You throw a container with calcium carbide and calcium phosphide into the water, They react, produce a bunch of gases, including phosphine, which then ignites when it hits the air, creating a super bright flare and smoke to signal for help. So we have one super stable element and one that's dangerously reactive. What's going on here? To really get this family's dynamics, we need to decode the underlying chemical rules that are making them act this way. This table right here basically tells the whole story. As we go down the group from nitrogen to bismuth, the atoms themselves get bigger. At the same time, the energy it takes to pluck an electron off, that's the ionization enthalpy, it goes down. So what's the takeaway? It's simple. As the atoms get bigger and puffier, their grip on their outer electrons gets weaker. It's like trying to hold onto a tiny pebble with really big, clumsy hands. It's just easier for that pebble to slip away. This explains the whole journey down the column.
But that brings us to the most important question. All these elements are in the same family, right? They all have the same number of outer electrons. So why is nitrogen such a weirdo? Why does it form that incredibly strong triple bond when none of the others can?
And the answer really comes down to just a few key personality quirks. First, nitrogen is tiny, and it's really greedy for electrons. Second, because it's so small, its atoms can get super close to each other. That lets them form that incredibly strong triple bond we keep talking about, that three-layered handshake. The bigger atoms below it are just too bulky to get that close. And finally, nitrogen is limited. It doesn't have these things called d orbitals, which basically means it can't form as many bonds as its bigger, more flexible siblings can.
Okay, so now that we understand the family's personalities and the rules they play by, let's do a quick lightning round on where we actually see them in our world. Because this isn't just theory, this stuff is everywhere.
Dinitrogen, our aloof giant, is incredibly useful because it's so unreactive. We use it to create what's called an inert atmosphere in industries to stop unwanted reactions from happening. And of course, as liquid nitrogen, it's an amazing refrigerant for everything from preserving food to cryosurgery.
Ammonia, that first product of tamed nitrogen, is, and this is no exaggeration, the cornerstone of modern agriculture. It's used to make nitrogenous fertilizers, things like ammonium nitrate and urea, that feed billions of people. It's also the starting block for a ton of other critical chemicals.
And one of those key chemicals is nitric acid. Using a really clever industrial method called the Oswald process, chemists can take the ammonia we just made and, through a few steps, transform it into this incredibly useful and powerful acid. And nitric acid is a total powerhouse. Yes, it's used to make more fertilizers, but it's also used to manufacture powerful explosives like nitroglycerin and TNT. It can be used to etch metals, and it's even used as an oxidizer in rocket fuels. Talk about a versatile chemical. So let's just step back for a second and bring it all together. From the harmless gas that makes up most of the air we breathe, to the reactive compounds and life-saving signals at sea, from the fertilizers that feed the world to the fuel that sends rockets into space, this one single family of elements is woven into the very fabric of our modern lives. And that really leaves us with one final thought, doesn't it? We've seen how the members of Group 15 can be both life-giving and destructive, incredibly stable and wildly explosive, all in the same family. It really makes you wonder, what other secrets, what other dramatic family stories are hiding in plain sight on the periodic table?